Hello?
Hello?
Hello, everyone. Looks like we're already online.
Hello, everyone. Looks like we're already online.
Let's get started. Can any,
Let's get
if,
started. Can any?
sorry, we got a bit of echo issue here. 1 second.
Sorry, got a bit of echo.
Okay, that's mine. Okay. Anybody in the live chat room, if you can hear us, could you give a reply? Okay, looks like we're good to go. So welcome everybody. Welcome to our third Launch and Learn session. So in this session, we have Dr. Ehsan Amjadian. He will be talking about the state of NLP in 2019. So as some of you may know, there has been a lot of advances that's been going on in state of NLP. So especially recently. So Ehsan will basically give you an overview and hopefully create some kind of mental map for you to help you better navigate through the landscape, and hopefully also so that you can when you are face your own task, you can have a better understanding of the task at hand. So for those, some of you may already know who Ehsan is. Ehsan is a friend of mine, and he is also Ehsan also received a PhD in um, deep learning, um, and especially in natural language processing and deep learning. And Aslan has more than a decade of experience in the field. He also published in IEEE and ACL before, and currently works as a senior data scientist at the Royal Bank of Canada. And he's also the head of research at Aggregate Intellect Incorporated. Aslan has developed many NLP and deep learning applications in his career and in academia. So without further ado, let's welcome Aslan. You can probably see him on the screen.
All right, beautiful. Are my slides here?
Oh, sorry. Actually, that's the other one, the Hangout window. The Hangout window.
Oh, okay. I think I.
Sorry, give us 1 second.
Huh. Okay. All right. Do we need to do anything?
Okay, let me share my screen. All right, we're good.
Okay, good. All right. All right. Do we want to start from the beginning? Yeah, all the way to the first slide. All right. Beautiful. All right. Thanks everybody for joining. I received a lot of good feedback on Reddit and elsewhere where we posted. People were engaged. For those of you who made comments and let us know what interests you today. Thank you for that. We had a good discussion around a few topics, and some people actually guessed correctly what are the important things that we were going to cover. Some of the topics that we're going to cover, it was a little bit harder to guess, but I think you'll see momentarily. Are we okay? I just need to. Okay, so yeah, so thanks again for coming over. Sorry, I'm just looking at my slides. All right. Okay, nice. Okay, so this is today's talk. Hopefully you see the slides. This is going to be a review. If you have seen review articles in the past, you know that in journals, those review articles address the general scope of the field and shed light on specific aspects of the field and the field overall, and sort of sketch where it has coming from and where it seems to be heading. And that's what we're going to do today. So this comes with a cost, and the cost would be we will miss minute details of architectures, which would.
Sorry, someone mentioned that there has been some echoing.
But that was in the past. Parham did, right?
Yes.
I think we fixed it.
We fixed it?
Yes, I think we
Okay,
fixed it.
let me check the
Yeah, I'm listening to myself. We fixed it. We're good.
Okay. Okay.
Okay, if you notice any issues, feel free to mention in the chat. All right, beautiful. So it was a rocky start, but let's keep on going. So yeah, so this is what we're going to cover today. We're going to talk about the significance of natural language processing, obviously very quickly and very briefly. NLP applications is an important aspect to incentivize those that are, not that, familiar with the field. But again, quickly, and modern deep search. That's one of the most significant part of today's discussion. And you get to know by the end of this talk what is this modern deep search, what's the classical deep search, and in NLP, and be able to distinguish them. Okay, state of NLP right now today, what is it? A classical NLP, we'll talk about them briefly. Oh no, we're still there. Classical deep NLP, we talk about it briefly. Application insights, we will talk about, and where to go next from here. Alrighty, so what is NLP for those who aren't familiar? NLP is natural language processing, so automatic processing of human language. Be it, so for some people it's just text, for some people it's also speech, for some people it's also other modes of human communication. But predominantly it's about text and speech signals. All right. So I think the most important dichotomy in today NLP is to draw between low-level and high-level tasks. So low-level tasks, well, let's start with high-level. So high-level tasks are those that you notice them as a human. You see them, you observe them, you know you're performing them when you are performing them. But low-level tasks, not so much. You wouldn't know that you're performing a POS tagging when you're speaking to your friend. So POS would be a part of speech tagging. Should I go back to?
No, no, you don't have to.
Okay. Yeah, so high-level tasks could be things like translation, summarization, question answering, and a lot of the industry, advertised applications of NLP. We'll get to some of them shortly. And low-level tasks are things like thematic role labeling, part of speech tagging, syntactic parsing, reference resolution. And you do all these tasks, but you may not notice them at the time that you're performing them. All right, let's move on. So this is to show you how omnipresent NLP is as a field, and language is everywhere in the industry, technology, and academia. Well, it's our main mode of communication as human. I thought I silenced it. 1 second. Okay. Oh, it's maybe you get to press this and then silence it. Okay. So yeah, so it's omnipresent, and these are a few applications of it. So sentiment analysis, reference resolution, and I hope at least you've come across with one of these tasks and topics in the past in your career. Sentiment analysis, reference resolution, spam detection, machine translation, speech recognition. Conversational agents, question answering, similar domain, document summarization, author verification, machine reading or machine comprehension or reading comprehension, video captioning, information retrieval, aka search, information extraction, which includes name entity recognition and term extraction, paraphrasing and paraphrase, so and paraphrase detection, text generation, automatic generation of text, and speech synthesis, optical character recognition or OCR, automatic entailment, handwritten recognition. So, and these are just to name a few. All right, so let's jump into the second surge in deep learning and NLP. So we'll talk about the first surge in a bit, but basically NLP has been redefined a few times. but maybe the most significant of it was at the presence of deep learning. If you want to go to the T0, maybe you can talk about reemergence of statistical NLP in late 90s and 2000s. But deep learning technically, but statistical natural language processing basically still tried to tackle similar tasks that rules just weren't good enough. Anyhow, let's talk about the second surge. We'll talk about the first surge in a bit. So very recently, from 2017 on, you see that this new architecture coming out. And if you haven't been following closely deep learning NLP architectures, you would be surprised at why are we doing all these things? Why are we talking about, I don't know, keys, queues, and queries, and values, and what's the point of all this? And then you would be lucky. And once you start reading all this work, you notice that there are so many different architectures already from 2017, and these are the prototypes of which that I'm showing you on this slide. So top left corner, you see the GPT architecture. Right below this, you see the Transformer XL architecture. Below, you see a comparison between a core part of three prominent architectures: Elmo, OpenAI, GPT, and BERT. Right on top, in the middle, you see the BERT architecture. Right after, you see LISA, linguistic informed self-attention. And then to the right, you see the core of all of this, which is Transformer architecture. So what is going on? And that's a very fair question. So we will cover some of the concepts. Each of these has a lot to be talked about, but let me tell you this specifically. It wasn't an abrupt change. It was actually, the transition was very smooth once you recognize the importance of attention. And almost all of these are relying on self-attention or attention in one way or another. So let me give you just a little bit of an overview of each of these quickly. So transformer network architecture, no, understand that, no worries. So transformer architecture on the right as a core tries to parallelize what we knew before as RNNs, gated RNNs. On one type of it are GRUs or LSTMs that were already equipped with attention. What we noticed is that one of the biggest bottlenecks of these architectures was that you would have words in a sequence or any types of other sequence. So if you've heard of sequence-to-sequence modeling or decoder-encoder architecture, you would, okay. So if you have seen sequence-to-sequence or encoder-decoder architectures, you would know that if you're dealing with a sequence, you encode the sequence one by one, step by step, from left to right or right to left, or both at the same time, form representation at each time step. And then at time of decoding, so when let's say you're doing machine translation, at the time of decoding, now when you want to generate the French equivalent of the English sequence, at each time step, so you start left to right, it's a language. Let's say you want to say, and forgive my French quite literally, if you want to say je suis étudiant, you start with je, and then at the time you want to generate suis or étudiant, you have to look back again in your encoding steps and see which part was important. What part of English, source English text or sequence is significant for me to translate at this specific point in time. or pay attention to at this specific point in time. So quite a few bottlenecks, right? First of all, it's RNNs. You need to take sequence step by step. So you can't just feed the sentence and expect an output instantly. And that was the biggest bottleneck. Well, one of the biggest bottleneck. There's another one that we may tackle. Bottlenecks, architectural bottlenecks, in RNNs and all the sequence-to-sequence tasks, which is the majority of today's advancements. Anyhow, so self-attention or transformer architecture is an exact response to that. I'm not gonna go too deep, but basically at each point, for each word, at the same time, self-attention forms a representation that is informed by every other word in the sentence. So whether it be self-attention, whether it be Elmo, or all the other architecture you see on the screen, one way or another do the exact same thing. Interestingly, they all tackle well multitasks and multitask learning, transfer learning, and perform much better in all of those tasks.
Just want to jump in here and say, I remember we have slides later to show the exact transition from MLP to RN, is it?
No, we're not going to do that.
Oh, we're not going to, okay, never mind.
Okay, wonderful. So let's carry on. And obviously, if you have questions about any of these, you can ask at the end. Or in the middle, Xiang is moderating today's session. Okay, so now what do they offer? So faster computation time, as mentioned, massive parallelization, meanwhile improving performance on a spectrum of NLP tasks, mitigating yet another substantial NLP bottlenecks, as mentioned earlier. Inherently address the issue of long-distance dependency. So long-distance dependency is if your sequence is just too long, well, without attention catastrophically, even with attention, it's hard to retain all the information coming from previous states. Attention definitely helps because at the decoding step, it lets you look back and directly consume the information presented earlier time steps. Okay, and highly efficient architecture with regard to the available compute power. So because we have parallel processing for matrix multiplication, basically, we can do our jobs of learning of training these deep algorithms much faster. Okay, so now let's look at the current state of NLP. Okay, so so NLP to date is divided into two categories: classical NLP and deep NLP. Classical NLP basically defines rule-based and statistical NLP. At the time, a little bit more than a decade ago, those were the two competitors. And statistical was arguably more autonomous. So the reason is in rule-based NLP, you have to have an expert to sit down and do all the rules for you, and you would be dependent on that expert the moment anything with regard to the domain or anything else, or the task or anything else changes, right? It's labor intensive. Deep NLP surge, I can say it started after 2010, 11, a very big hip, and then a very big jump, and then 12, it established itself, and then all the way through to 2019, it's been improving and transforming into modern deep NLP. All right, so let's tackle these. So rule-based NLP. These are quite a few of the contributions. So when I talk about all these paradigms in NLP, it's not meant to say that something is useful or more useful than the other necessarily. It's just we need to know all the paradigms in order to use them proficiently, right? So rule-based NLP enabled us to achieve very quick success in tasks that could be governed by rules very quickly. To date, even the best machine translation systems, in some way or another, are still using the rules. So let's not at all downplay the significance of these rules. But it started with finite state automata, regular expressions and regular languages. And bottom left and top left, you see these automata. You also have transducers that would also generate. So automata were used to detect if a string, I don't know, is a verb, is a past tense, right? And then you could use transducers to generate. And then in the middle, you see the word net. So that is the word net from the point of view of the verb be. And then you see all the clusters of different words around it. That's fascinating. And
B as in the word be.
as the word be.
Link verb of be. Okay.
Yes, the link verb be. Thanks for that. Yeah, not the one that makes honey. And on the right you can see derivational rules, so phrase structure rules, otherwise known as, that will sort of sketch the syntactic architectures, because human language is hierarchical, and to do that used linguists for a long time used phrase structure, or these tree data structures, and they were all big contributions of natural language processing. At the beginning, rule-based natural language processing, and then statistical NLP used these data generated a lot of times by humans, and created its own algorithms that would a lot of time beat the earliest stage algorithms. All right, so these are a few examples of statistical NLP now. If you remember, we're covering the tree. So in the tree, we talked about non-deep NLP and NLPs, and we talked about, and then the former would contain statistical NLP and rule-based NLP, and then deep NLP would contain classical deep NLP and modern deep NLP. All right, so we're at the statistical NLP. We're still in the classical NLP section. Okay, statistical NLP, quite a few advances. Here are just naming a few. It relied heavily on word co-occurrence. So you see the word co-occurrence matrix on bottom left. And then it would form some representations a lot of time out of it. You see in the top sketch of factorization for topics and documents. Or this is words and documents, but it can also be used for words and words. If you have word-word co-occurrence, then you would construct your currently known embeddings or dense representations, right? If you factorize the matrix, well, dense as it can be, because it all starts with the sparse matrix. And that was one of the biggest bottlenecks over there, because you would come up with this very big sparse matrices, and you had to create dense representations. All right, or do document classification. All right, beautiful. So on bottom right, you see something known as hidden Markov models, right? And it actually built on top of the formerly known finite state automata. Just it was mingled with probability theory, as well as a few very good algorithms, including Viterbi algorithms, to decode. Anyhow, with hidden Markov models, we built very good POS taggers, part of speech taggers, and any of the sequence labeling tags that you would know. All right, beautiful. So let's go to the next slide. Okay, the deep search finally. Okay, it happened around 2010, and going forward. And maybe a little bit earlier, but it took a little bit to catch on. And these are the most prominent works at the time. So let's start right at the middle. So the middle is the original neural language model by Yoshua Bengio. Amazing work. I read the article. At the time, it blew me away. Basically, what it does is it uses the multi-layer perceptron architecture, or the fully connected architecture, to predict the next word coming up in a sequence, which is crucial in language. In doing so, it backpropagates the errors to the earliest layer. You see the layer at the CW, forming a representation. So the first known, or at least caught on, embedding representation was but this work. So nominal work, and the beginning of the NLP search. So the problem with that was that it had quite a few bottlenecks, including using a fully connected layer, which is a lot of multiplication to go through. And also the softmax layer is a vocabulary size. That's a very big bottleneck. All right. Then on the left, you can see, okay, maybe there is a more efficient way to encode sequential information, then therefore the emergence of RNN. So top left, that's the vanilla RNN. Issues, first, vanishing exploding gradients.
Sorry, could you just tell, like, for those maybe not familiar, could you tell like roughly how it works?
Yeah, absolutely. So on the left, you see a folded version of RNN, and on the right, you see that it unfolds, right? Basically, at each time step, it takes in an input, and then can spit out an output, or just form a representation, depending on your application. So if it's a language model, you may want to go through xt-1, xt, and then predict the word coming up in xt+1, right? So that's the RNN. No gates, no attention mechanism. It was just a bare RNN at the beginning.
So the difference between the RNN and the multi-layer perceptron in the middle, what is the main advantage of RNN to the left?
Yes, as I was going to say, RNNs architecturally encodes a sequence. At each time step, it knows each time step is a different one, right? Okay. So and it occurs right after the other. So therefore, your information is coming in sequentially. Therefore, it's encoded sequentially, as opposed to fully connected layer, which takes in the information all the time, and then you can still define time steps or generate, but not much distinction between your input layers. Okay, beautiful. So you inherently architecturally encode a sequence, and it is very efficient because you're not multiplying everything by everything. You're just doing one multiplication at a time when you get the input. Well, two, because you also transfer the hidden state from the previous time step. Flaws. One would be vanishing exporting gradients. So there is no mechanism to prohibit your gradients, from blowing up or from vanishing altogether. If they go to zero, well, nothing gets up. You just stop learning, right? One way to mitigate that would be using. Is there something happening? One way to mitigate that is using LSTMs. You see bottom left. LSTM, or long short-term memories, have these different memories interacting with each other via gate, namely input, forget, and output gates. Each one happening at a specific time, and gating hidden states and the inputs and transition to the next cell in the sequence. So you have a lot of power to amplify information early on and dampen information at the moment, or vice versa. So, and it did indeed help both with the performance and vanishing and exploding gradients. Amazing. So on the right, top right, on the right in general, you see two of the most prominent quote-unquote embedding architectures. That the advantage of those is that they're just super fast. All you need to do is a linear projection. That's all you need to do, and it is just very fast. You can run them on CPUs, um, and form very good representations of your words and your domain, and then use transfer learning, use classifications on top of it. Um, Okay, so the first and most the most famous one is Word2Vec. You see top, and there's the skipgram and CBAR architecture. Most of you should be familiar with it. If not, ask and I'll talk about it. Bottom is glove. The way Word2Vec was, it works with sliding windows. You have your text, you go through your text via sliding windows. So therefore, you may use long distance information, right? A word may occur all the time with another word, but not just in the window size that you recorded. So Glove tackles that issue by sampling from the co-occurrence matrix directly. Okay, then what's the difference between Glove and LSA? Because in LSA you also
Sorry, what is LSA?
latent semantic. I was going to say so latent semantic analysis. In LSA you also form the co-occurrence matrix, right? And from the co-occurrence matrix, you would create somehow dense representation by matrix factorization, right? As was shown earlier on in the statistical NLP era. So the difference is that it samples. When you sample, you don't face much of a bottleneck. Is that clear? Mm-hmm. Okay, beautiful. So that's Glove, and that's Word2Vec. Glove came out after Word2Vec, and it performed better. But they both are used interchangeably today. All right, amazing. Now, what to use when? So, to give a comprehensive account of here are these many tasks, and then use this algorithm or the other, across the spectrum of algorithms I just talked about, it takes hours, if not days, right? And we can talk about the specifics and all the time, but I just give you a few samples, and then if you have other questions, feel free to ask, and we'll talk about them. So the first thing in today's computation, like one of the important things in today's computation is your just compute power, right? Are you working with GPUs or CPUs? Are you working with clusters of CPUs or clusters of or just a few machines or just one machine? And what's your network capacity? Okay, so basically, if you're using GPUs in dev as well as in prod, go all the way to transformer networks, because they're fast with GPUs as compared to other deep architectures, and they perform really, really well. The only catch is you need to have some data. Hopefully the data is at least tens of thousands, or hundreds of thousands and millions. If not so, you can still do methods such as transfer learning and get away with it with 1,000 or thousands. But over there, you got to be very, very careful with your validation procedure, and you got to have a very strict validation procedure, making sure that your trained model has not overfit and can generalize. And there are quite a few, and we can talk about it in hours. So if you have GPU in dev but CPU in prod, again you can use transformers to train. With the cost of high latency during your decoding. If you have multiple CPU clusters, CPUs in your prod, and for those who aren't familiar, like maybe are coming from academia, dev is your development environment, prod is your product environment. There are many differences. And a prod is usually security-wise very strict. And dev is for running and testing things, so you have a lot more flexibility in your environment, and also many other differences between the two. But anyhow, if you have CPU in prod but GPU in dev, if you can afford the cost and you can add a cluster of CPUs, then you can still get away with using GPUs and have very fast training. One way to mitigate the slow runtime feedback would be using lower parameters. So just don't blow up your parameter space. All right. So CPU in dev and CPU in prod. So deep learning in general not recommended. You should not touch anything deep learning. I have trained deep learning architectures, very recent by LSTM architectures in CPUs, but you use very small parameter space, and then you would need weeks to train your model and make sure it's good. At the very least days, and it's not efficient for agile prototyping. Okay, so let's move on. Is my architecture data dependent? Um, so basically, I hear that a lot out there. So people talk about architectures. Oh, if you have this much data, use this architecture. If you have this much data, use that architecture. It's not about architecture. It's about your parameter space. It doesn't matter which architecture you use. If your parameter space is large, then the architecture is, no matter what architecture you're using, um, you may not have enough to generalize. You may definitely overfit, right? Or you may not just learn enough. Um, well, if you're I think it's important just to note that. So whenever people say, oh, if you have this much data, use that architecture, like they yes, transformer architecture by default uses bigger parameter space, right? But it's up to you. You remember, you initialize all these architectures, so it's up to you. You can have a transformer network with smaller parameter space than an RNN. So it's up to you, and it's about parameter space. If you have smaller parameter space, then you can use less data to train, right? At the cost of learning well. Okay. Then the last point. Yeah, I already responded to that. Okay, beautiful. So why do I need to know, as a today practitioner, data scientist, machine learning scientist, or NLP engineer, or machine learning engineer? Why do I need to know the details of the architecture? Can I just grab it out of the box and use it and get it off GitHub, or use it out of the packages that these linear algebra libraries such as PyTorch, TensorFlow offer? I mean, you absolutely can, but can you use it to its fullest potential? Or can you make sure which architecture is good for what without knowing what's going on inside? Or can you predict which will work better on your specific task? And now, in a more realistic scenario, can you actually customize it and adapt it towards your task without knowing what's going on under the hood? So it's very challenging. And so it's very important to know what all these nuances are and what are the costs of your choices are in advance. Of course, you have to go ahead and prove your hypotheses, but you need to have some hypotheses. Okay. So basically, yes, if you're a data scientist, ML scientist, NLP engineer, research scientist, so on and so forth. Okay, I should just say that. Oh, okay. All right. So now just okay. So I think I mentioned all of these points. Okay, let's go to the next slide. Okay, do I need to know? I already said that, right?
Right.
Okay, beautiful.
Okay. So before we, I think, move on, let's pause a little bit and ask if anyone has any questions. I think Ernest actually asked if quantum computers potentially have any place in this space?
Yeah, absolutely. Thanks for the question. So they will. It will take a while for quantum computing to. I think we're in quantum computing in general, and I'm not a quantum physicist or a quantum computer scientist. But a very good friend of mine is, and we talk about it all the time. Also, people who are experts in our community are. So my understanding is that quantum computing is at this stage that requires two different advancements to be as highly available as traditional computers are. And the most important one is that it needs to be a universal computing machine, which they aren't. So most of the time they're task specific, algorithmic implementations. So that's one. A lot of advancements. Sometimes you see very big advancements in a very narrow area in quantum computing, which is amazing, but it renders for now inapplicable to the very to the current problems that we have. So, a short answer yes. In the future, as we have large enough qubits and we have universal computing machines, it would be amazing. Otherwise, specific tasks. And remember, even for the specific tasks, transferring to quantum space can be costly. And so there are bottlenecks to be taken care of, not in the next decade, at least at very least. I've been generous here.
So, Supriya, I hope I said the name correctly, it asks, so training needs labeled data, um, right? Are there any unsupervised techniques in deep learning for NLP?
Oh, absolutely. So, and that's the beauty of it. You have quite a few ways to get rid of the need to the extent that's possible for every task that you have. So one way is unsupervised learning. If you know about, if you have heard of the autoencoding architecture, basically your data is your input and output at the same time. So you try to form a representation of your data. Um, Similarly, other NLP platforms use the same concept to reduce the size needed for labels, including language modeling, for example. Each word coming in the text is itself the label because you see the history, you want to generate the next word. So I think unsupervised learning, well, it's still supervised, so it's in the middle, but you have the labels there because you're using your data as labels. Is used across in NLP. Um, but this reduces the number of labeled data you need, basically by what is known as transfer learning. So for a hand on that representation, create a few data points, I don't know, thousands, and then you can train your network. There are so that's when people say unsupervised deep learning, usually that's what they mean. There are inherent unsupervised algorithms that we talked about. Most of them came out of the statistical NLP era, the co-occurrence matrices and LSA and topic modeling. But for deep learning, you need to have some form of labels, and you can be smart about it.
So, Rosebeth, did I say the name correctly? Yeah.
I hope so. I can't read.
Rosebeth. What do you mean by architecture is not data dependent? When you say data, when you say data are when you say data, are you also considering things like sequence length? Oh, when you say data, are you also considering
Okay.
things like sequence? Sorry.
Right. So I see that it can be. So what is meant by um, architecture? Data isn't architecture dependent. Yeah. Is so. What is meant is that for a given task, usually what happens, and it's a lot of noise out there. People saying, "Oh, if you have this much data, use this architecture. If you have more data, use this other architecture. If you have more data, use this other architecture." And by architecture, I mean the types of architecture that I discussed. For example, RNNs, LSTMs, GRUs versus transformer networks. What I'm trying to say is that it's not about your architecture, not necessarily when you talk about the data, size of data. So by data, I mean the size of data. It's about your parameter space and the performance you gain from it. If you have a large parameter space, you need more data. Otherwise, you won't be able to use your parameter space to its fullest potential. Therefore, you would have been better off just with a smaller parameter space.
But for if you have very long sequences and then Uh, is it fair to say in that case that somewhat limit your architecture choices?
Oh, of course, but we're talking about we are talking about the data size specifically. That's an orthogonal point. Yes, your sequence length can to some extent define your architecture. If your sequence is very short, then do you really have to go and use Transformer XL architecture? By the way, Transformer XL also was in our image. I didn't go over it. It's one of the biggest architectures. So yeah, absolutely. Your sequence length, you need to be aware of your sequence length as well, because that would define your encoding and decoding steps as well, and how you bin your data points. As I mentioned, this is more of an overview, and it's not easy to cover all the details there is in NLP in such a short time.
Okay, so Owen is asking, do we need to know the classic NLP approach, such as sequence-to-sequence RNN, to learn more about the recent advances, such as Transformer, GPT-2, etc.?
Okay, they can give you great insight, but no, you do not. In fact, I'm going to talk about it. So in a future workshop that I'm having, I do not cover the specifics of the classical NLP. They can give you great insight as to what's happening, and you see repetition. You see history repeating itself just in a different form. But you don't need to if your goal is to learn the modern deep NLP per se, some of which gets repeated. VRB algorithm is still being used in decoding, but other than that, no, you don't have to. But if you're an NLP engineer or a data scientist at work, not just for study purposes, then you have to know, because if you can, if you can just address the problem in 5 minutes, what would you spend weeks to solve it? So it's a matter of picking the right tool. You absolutely need to know if that's the case.
Okay, if there's no other, okay, so there's another question from Bing Tao. Could you recommend and post a link of NLP course here? Thank you.
Okay, so that's a very good question, and it will transition smoothly to what we're going to talk about. Okay, so more to come. All right, so we will have a modern deep NLP workshop. I'm very happy about the questions that were asked, because it is a question that people ask me almost on a daily basis. Okay, what do I need to study? Which part of it should I know better? What should I invest in? Do I need to know classical? If not, what parts of it is interesting, right? And there is a lot of noise out there, and some good information, sometimes a lot of misinformation out there, right? Some of which I clarified today. So we have, as Aggregate Intellect, we have formed these workshop series. So this is going to be the very first of the NLP workshop series. This is coming up on the 27th of this month, June. And we will address all of that. So we will give you. So the workshop is called Modern Deep NLP. I think it has a prefix of premium technical workshop, but basically over there we cover a lot of the concepts that can just get you jump start in the modern cutting edge deep NLP. Assuming that you have GPU access, because that's usually, if you want to be competitive in the industry, you need those. We teach you all the tricks that are there, with regard to how to get your model in dev and to production. So everything end to end we do talk about, but the focus are these concepts and more. So agile deep learning. There is a lot of almost every company that's successful and is very intentional about the steps that they take. They're using agile in one interpretation or the other of it. And how do you use it for deep NLP? Transfer learning. We start off the bat with transfer learning and get you hands-on experience on transfer learning. Details of equation and the code. So I did talk about the overviews today. I did not cover every detail that there is and all the math that there is to it, but basically I was telling Xiang, like basically whoever takes this workshop will do the math in their sleep easily. Because it is, after all, it is easy. Like I'm against the general conception that the math is hard. No, 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 it's easy. You just need to have the right context, right? Okay, so implementational details and tricks we talk about. Overcoming the bottlenecks. What are the bottlenecks? What are the bottlenecks that have already been tackled? What are the bottlenecks that have not been tackled? I talked about the math. Two more points, and I'll be available for the.
Right. So actually, there's a related question.
Okay.
VV11 is asking, is workshop 50% theory, 50% practice?
That's almost very accurate. We intend for it to be so, but like if it's 51%, I can't really predict. But we intend for it to be so. So it's 50% theoretical and 50% hands-on. So whatever we talk about theoretically, in the math and in the algorithms, you see in practice in your code, and you code them. And you've at least gone over on the architecture once, or any of the architectures once from theoretical perspective and implementation perspective.
Okay. We have one more question, but before we try to answer all the questions that people have. But let me just mention briefly that we're providing an extra 5% discount to those who want to register for the workshop in the next 24 hours. So we do have some kind of a tiered pricing setup, so that towards the end of the the closer you register to the workshop date, and I think the higher the prices is. Like if you register now, then there's a less discount. In addition to that, we have a
there's more discount if you purchase now.
Right, and in addition to that, we have extra 5% discount if you purchase within next 24 hours. So someone is ask another question, which is Ali Reza is wondering about the explainability. Like, is there any research on NLP explainability similar to AI explainability?
Yeah, absolutely. So I would say that in general, AI explainability is very, very transferable to natural language processing. So all the salience testing and all the methods. So basically, so some people say that, oh, deep learning, well, used to say that. I pretty much believe, thanks to all the research work these days, less so, and maybe it came from people not understanding what deep learning is. Deep learning was infamous for not being explainable, but I don't think that's necessarily the case. It just enables deeper layers of explainability. So I give this example all the time, like receptive fields. You couldn't see that early. Like you see a receptive field of a CNN, and you can explain which part of the image that neuron is reacting to, right? But to get to your question, almost everything that's used outside natural language processing algorithms is nowadays, thanks to the omnipresence of deep learning, is transferable directly to natural language processing. But it does have some, advantages of its own, because we're talking about words. We can see what words at each time step your algorithm is paying attention to. Okay, so let me go quickly through the next two, and then I'll take other questions if there is more. So I just want to make the point. So there is the significance of the workshop coming up is that it is the core modern deep NLP. If you know it, this is going to be a series. So other workshops, we're going to talk about specific applications. AI and explainability is actually one potential workshop that we're coming up in this series. And applications could be, summarization, machine translation, speech recognition, deep sentiment analysis. Anything that you may think of we're gonna do follow-up workshops on, and that's our plan. And this core NLP workshop will enable you to progress super fast in those other workshops, and be super successful. But given that the workshops are interdependent, so if you lose this one, it's not the case that the last one is going to be inaccessible too. We try everything to be accessible. Just attending this one will diminish the learning curve for the next ones. Other ones, you still be able to follow any other workshop that comes up. You just be maybe a little higher learning curve.
Okay, we got quite a few questions about the workshop itself, but I'm just going to group them and answer here. So a lot of a few folks asked, what kind of preparation do I need to do? We will send out a list and maybe some exercises to make sure that our attendees are come prepared. So there is actually a prerequisite for Python and
Yeah.
linear algebra. Is that correct?
Yes. So if you check we can send. I'll leave as a comment the page for the Eventbrite, and over there you see that you need to be familiar with Python absolutely, and you need to have familiarity with linear algebra. It's hard to go again and refresh all the linear algebra, but if you have taken linear algebra in the past, and if you're familiar with Python, you should be covered for the most part. Yeah.
Okay. So I think there's another. Someone asked another thing about workshop, but if, I think it's in terms of location. If you're in Toronto, we do offer. It looks like we're very close to enabling in-person workshop. I say it's pretty much a certainty at this point. So we will have a session in Toronto, and we will at the same time live stream online. So there are like different ticket classes. If you go to the Eventbrite page, I think okay. We posted it in the chat and we leave it in the comment. If you go to the Eventbrite page, there are different ticket classes. So your options are either attend online or attend in person. But if you're around the Toronto area, we highly encourage you to attend in person. In fact, we actually have attendees said like I only want to attend in person, but I think that's a matter of like people's choice. But we'll make sure that that message is delivered like both in the format of in person and online, so they have a good experience.
Yeah, so teaching assistants will be available to to everyone, whether online or on site. But if you're on site, then you can just, you have the privilege to stop me anytime, ask questions, like if you forgot that, that calculus, I don't know, derivative, and then you can just ask right away, or any other algorithmic question. From online, it gets filtered by the TAs. It's just a little more convenient. So if you want to be in person, that's available too. If not, if you want to work from tune in from home, or if you're far from Toronto, if you live in another country also, you can tune in via our gated streaming.
Okay, so time is 1 o'clock, so regrettably we need to wrap this up. And thank you all for the questions, and thanks Ehsan for the great talk today. And so if you have any further questions, feel free to shoot us an email at events@ai.science. That is our email. Okay, thank you very much. Or you have any further questions, you can shoot us on Slack if you're a member. It's all a lot of you know us, so we definitely anytime feel free to ask. Okay, thank you very much again for coming, and until next time. So this is Xiang and this is Essam. Bye everyone.
Bye everyone.